Greetings and welcome to Precalculus, Polynomials and Rational Functions. In this lesson, we're going to focus on the complex zeros of a polynomial function. All right, first and foremost, we need to remember what a complex number is. Let's let some number z be in the form of z equals a plus bi. Then this is a complex number where a and b are real numbers and I is the square root of -1. Now, we're going to deal with a polynomial where when you put this complex number in, it equals 0. So that means it's a complex zero. So just like we have real zeros, we're going to deal with the complex zeros. We have a really cool theorem, and it's the theorem of the fundamental theorem of algebra. For every polynomial function in this form where we've seen it before, I'm not going to read it out, for every complex coefficient of a sub n minus 1, all the way down to a sub 1 and a sub 0, it has at least one complex zero. And now we have the factorization theorem of polynomials, which will help us understand that these complex zeros come in pairs. If we have our complex polynomial of some degree, and with some degree of n being greater or equal than 1, and our leading coefficient is a, some value, it can be factored into n, not necessarily distinct, factors in the form of p of x is now going to be a times x minus r1, x minus r2, all the way down to x to the rn. And this r value, including the a, are complex numbers. Now, these aren't necessarily distinct values, but they are complex values. We have another theorem that, remember, all of these theorems are going to help us solve problems faster than it would if we didn't have these theorems that we're falling back onto. So our number of zero theorem is any polynomial of degree n has exactly n zeros, provided a zero of multiplicity m is counted. So if for example, if our polynomial has 2 plus I and its multiplicity 2, we need to count that twice, and it has exactly n zeros. All right, enough talking about theorems, enough looking at words. Let's actually run through an example. Let's construct a polynomial given we have the zeros. So let's find a polynomial of degree 4 with leading coefficient of 2 and the zeros of -1, 3, I, and -I. All right. We want to do it two different ways. One, in completely factored form, which would be the easiest way, and then by expanding it to where we have something that actually looks like a polynomial. So in factored form, what we're going to do is we're going to plug in our zeros. So -1, 3, I, and -I. Now remember, this is going to be x minus each one of these in factored forms, and we do have the leading coefficient of 2. So here is our factored form where we have a, x minus r1, x minus r2, x minus r3, x minus r4. For r1, r2, r3, r4, we're going to plug in our answers, our zeros. And for our a value, it's that leading coefficient of 2. So let's plug all of those in. Now we get 2 times x minus -1 times x minus 3 times x minus I times x minus a -I. Now I'm just going to clean it up a little bit and change those minus negatives into positives. So we end up with 2 times x plus 1 times x minus 3 times x minus I times x plus I. Now the way that I'm going to do that, this is completely in factored form. But now we need to do it and expand it to where it looks like a polynomial of degree 4. So here we go. How I'm going to do it is I'm going to kind of group some stuff together. And for me, that's the easiest way to do it. Probably group the x plus 1, x minus 3 together, as well as x minus I and x plus I. And then I have to deal with the 2 as well. So I might bring that in first and then deal with the groups and then pull the groups together. How you decide to do it, if you literally decide to do the 2 first, then the first 2 terms and the second 2 terms, it's up to you. This is just multiplication. So I'm going to do it in the 2 groups, the x plus 1 and the x minus 3 together, and the x minus I and the x plus I together. And I'm just going to use foiling to do this. And I'm going to end up with, for the first one, x squared minus 2x minus 3. And in the second one, I'm just going to run through this one from the start. X times x is x squared. X times positive I is xi. Negative I times x is negative xi. And negative I times I is negative I squared. The 2 things in the middle drop out, and I have x squared minus I squared. But you have to remember, I is the square root of negative 1. So the square of square root of negative 1 is negative 1. So I have x squared minus negative 1, which turns out to be x plus 1. Bringing these all together, and don't forget I have that 2 in front, I have my polynomial is 2 times x squared minus 2x plus minus 3 times x squared plus 1. Now, I'm going to go ahead and multiply 2 through, and I get 2x squared minus 4x minus 6. And now it's just foiling it. Each term has to be, in the first term, has to be multiplied by the second term. 2x squared times x squared is 2x to the 4th. 2x squared times 1 is 2x squared. I probably did all the first, so let me start over. 2x squared times x squared is 2x to the 4th. Negative 4x times x squared is negative 4x cubed. Negative 6 times x squared is negative 6x squared. Now, let's do the rest of it. 2x squared times 1 is 2x squared. Negative 4x times 1 is negative 4x. And negative 6 times 1 is negative 6. Now I'm going to combine like terms, and I end up with my polynomial expanded. It is degree 4 with a leading coefficient of 2. 2x to the 4th minus 4x cubed minus 4x squared minus 4x plus 6. It's a mouthful, but if you take it step at a time, it shouldn't be too much of an issue to pull this all together. Now, I kind of talked about it already, but we have what's called a rule, a theorem that says when we have a complex number as our 0, we also have its conjugate, and we're going to say our conjugate is if we have some complex number z equals a plus bi, then also one of its 0 is the conjugate. Just put that little line over it to say it's the conjugate, and that equals a minus bi. The only thing that changes is the middle. If we're an addition, we go to subtraction. If we're a subtraction, we go to addition. So those two come in pairs. If one is a 0, the other is a 0 as well. Odd degree of polynomial have a real 0, because remember, if we have complex zeros, those come in pairs. So of course an odd degree is going to have one left over. Even if all the other pairs are complex, it has one left over, and therefore we have at least one real 0. We might have more, but we have at least one because all the complex answers come in pairs. So let's think about it. You know, if you have pairs and everything comes in pair, let's say we're working with a degree of 5, and I have this pair of complex zeros, and then I have this pair of complex zeros. Well, the remaining 0 does not have a pair to go with, and therefore it must be a real solution. So let's use this conjugate pair theorem in action. So we have a polynomial, we'll just call it Px, P of x, and it's to a degree of 9 with real coefficients has the following zeros. 2 with a multiplicity of 3, 4 plus 5i with a multiplicity of 2, 3 minus 7i with a multiplicity of 1, and we want all 9 answers here. All right. Well, right now we're only given 3, 4, 5, 6 answers. We're missing 3 of the zeros. All right. Well, 2 has a multiplicity of 3, so it would be 2, 2, 2. 4 plus 5i has a multiplicity of 2. That means that we have to pair it up with their conjugates. 4 minus 5i also has the multiplicity of 2. And then 3 minus 7i has a multiplicity of 1, and therefore its conjugate, 3 plus 7i, also has the multiplicity of 1. Now let's just count these out. 3, 4, 5, 6, 7, 8, 9. And here are all the 9 zeros. 2, 2, 2, 4 plus 5i, 4 plus 5i, 4 minus 5i, 4 minus 5i, 3 minus 7i, and 3 plus 7i. Those are all 9 of the zeros. Okay, I know another theorem. Not that you wanted one, but we do have another theorem. It is called the Factorization Theorem for a polynomial with real coefficients. For every polynomial with real coefficients, it can be uniquely factored over the real numbers as a product of linear factors and or irreducible quadratic factors. Now, it might not sound like that's very helpful, but it will be helpful. Just hang in there. Finding the zeros of a polynomial given complex zeros. So given that we have 2 minus I is a zero of this polynomial, P of x equals x to the 4th minus 6x cubed plus 14x squared minus 14x plus 5. We want to find the remaining zeros. Okay, we are given one of these guys. Well, we can find another one very easily because remember, these guys come in pair. This is a complex zero. So we know that 2 plus I is also an answer, a zero. Okay. All right. So we know that we have 2 of our 4 possible solutions, 2 minus I and 2 plus I. Okay. Because we know that 2 minus 2 minus I and 2 minus 2 plus I, what I can do is I can FOIL this out and I can see what polynomial this is. So x times x is x squared. X times 2x times a negative 2 plus I is minus x times 2 plus I. And then negative 2 minus I times x is a negative x times 2 minus I. Now you might be wondering, why didn't I do each individual? Well, you'll see it's a little bit easier to keep it grouped. And then finally, negative 2 minus I times negative 2 plus I is plus 2 minus I times 2 plus I. I am eventually going to have to distribute these external coefficients in there, but I find that it was easier, instead of doing all these little steps, is to go ahead and keep it as a blob in parentheses. All right, now I'm distributing everything. Negative x times 2 is negative 2x. Negative x times I is negative xi. Negative x times 2 is negative 2x. Negative x times negative I is positive xi. And then when I FOIL, I get 2 times 2 is 4. 2 times I is 2i. Negative I times 2 is negative 2i. And negative I times negative I, negative I times positive I is negative I squared. We're going to combine like terms. And we get x squared we have negative 2x, and negative 2x is negative 4x. The negative xi and the positive xi drop out. The next thing we have is a 4. The 2i and the negative 2i drop out, and we have left as this negative I squared. But remember, I is the square root of negative 1. So really, the square root of negative 1 squared is negative 1. And a minus negative 1 is a positive 1. And I have to put together the 4 and 1 and to make 5. All right, so we ultimately get a factor of x squared minus 2x plus 1 when we combine all of this. Now I'm going to do some long division. Now you could have done synthetic, but I'm going to do long division so I can see what else I get. Oh, that's not right. So we ultimately get x squared minus 4x plus 5. Now I'm going to do some long division. Now that I have this factor, now I know it came from 2 factors, but I have this polynomial, I'm going to divide the x squared minus 4x plus 5 into my original polynomial. And I get, and I'll let you look at all the work that I've done here, and I ultimately get x squared minus 2x plus 1. If I factor this x squared minus 2x plus 1, I should get the other 2 zeros. Okay, let's factor x squared minus 2x plus 1. Well, positive 1 means that they both have the same sign. 1 times 1 is 1, but 1 plus 1 is 2, so they've got to be negative 1s. And therefore, my remaining 2 answers are x equals 1 and x equals 1. So to find our our zeros of p of x, we were given 2 minus I. Using the conjugate theorem, we found 2 plus I. And doing some combining, multiplying, and dividing, and factoring, we found our other 2 solutions of zeros of 1 and 1. I know that's a lot of work, but do the steps slowly. You shouldn't have a problem with them. Let's again find zeros of a polynomial. Now we have a new polynomial, x to the 4th minus x cubed plus 7x squared minus 9x minus 18. Now we're degree 4, so we really should think about we have 4 zeros. Okay. Next, let's think about all the rational zeros that might be possible. Our leading coefficient is 1. Our constant is 18. So we need to factor both of these. So for the factors of 18, we get 1, 2, 3, 6, 9, and 18. And of course, we want both the positive and negative of these. For 1, well, we only have one option, plus minus 1, or I should say 2 options, but we're going to ignore the negative. So 1 over all of them means that we have the possibility of 1, 2, 3, 6, 9, 18, both positive and negatives, as our solution, at least for our real solutions. Now I'm just going to start with 1, 2, 3, 6, 9, and see what we get. All right, so 1, and using synthetic division here, I get a remainder of negative 20, so that is not one of our zeros. We get 1 for our second 2, for when we work this out, we do get a remainder of 0. So 2 is a 0 of the polynomial, and that last line is all positives, meaning 2 is our upper bound. We don't even have to check 3, 6, 9, or 18. That is our upper bound. All right, so let's pull this factor of 2, meaning that we have x minus 2 as a factor of our polynomial, and we are left with 1x cubed plus 1x squared plus 9x plus 9. Okay, now I'm going to go ahead and try and factor this guy and see what happens. I'm going to group them and say, okay, well, x cubed plus x squared, they have an x squared in common. 9x plus 9, it has a 9 in common. and I end up getting x squared times x plus 1 plus 9 times x plus 1. They both have this x plus 1 in common. And so I'm going to factor it out. And I get x plus 1 times x squared plus 9. Okay, cool. Now, here's what I want to do. I can rewrite our original polynomial using our factors. We have x minus 2, x plus 1, x squared plus 9. Okay, I know that x minus 2, that gives me an answer of 2. I know my x plus 1 will give me x equals negative 1. And when I go ahead and take the square root of both sides, I end up getting, move the 9 over, I get x squared equals negative 9. Square root of x squared equals plus or minus the square root of negative 9. We can pull that negative out and make it the square root of negative 1. And I know what the square root of 9 is. I know what the square root of negative 1 is, which is I. So x equals plus or minus 3i. So all of my zeros for p of x is going to be negative 1, 2, 3i, and negative 3i. Now that's it. You can use all the techniques in our previous finding the zeros of polynomial, our previous lecture, and still apply it here. It's just you're going to hit a point where when you're dealing with complex numbers, you will have complex solutions. Or even if you're dealing with real values, you might come up with complex solutions like we did. All right, that's it for this video. Quick one. Until next time, be seeing you.